Thank you very much for inviting me. Thanks to the organizers for setting this up. Very nice. So today I will talk about deconfined criticality, which we have already heard a lot about. So hopefully I don't need to give a big introduction. So I will look at a lattice model, and John already talked about the JQ model, so the transition from NEL to VBS in different kinds of JQ models, actually. So this paper just appeared last night, in fact, just pure coincidence, right? So this is also my way of introducing my co-authors here. So Jun Takahashi, he was my postdoc a few years ago, and now he has been at the University of New Mexico for a couple of years, and he just moved back to Japan now. And Hui Xiao, she's also a former postdoc, now professor at Beijing Normal University, where Wenan Guo, my long-term collaborator, is also. Bo Wen Zhao is a former PhD student from BU. Okay, so this is actually a very long paper, so today I'm just giving you some, a broad overview of the main parts, and if you want details, you can look at the paper. So John already introduced the JQ model. In his case, he introduced the JQ2 model, which is combining the Heisenberg exchange, which is just, a singlet projector of two spins, with this Q term where we take products of two singlet projectors. But we can do more singlet projectors. So now we have QN models that we normally think of as, these projectors arranged in a columnar fashion like this. But we can also do some other arrangements. This one I call Z, kind of looks like a Z, maybe a little bit. So, these models I will show results for. So what we are doing here is to basically test this scenario that Shai talked about, a critical point with two relevant symmetries. But actually this had been going on for several years. But when we saw the paper by Shai and Ning Su, then we realized that this basically how we should identify correlators and operators in a way that we had not done before, so that was very helpful. So as he explained as well, when we think of emergent SO5, we expect that we should have actually an SO5 relevant singlet and also this traceless symmetric tensor, which corresponds to an operator that takes you from the NEL to the VBS, right? So changing, violating the SO5 symmetry. So now we have some possible phase diagrams. Here are two, natural ones that you could imagine in the plane of T and S. So this isolated critical point is at 0 here. So then, we could have a first order transition here and then ending at that one. And then there could be a generic VBS AFM, continuous one here. But it's also possible, and there's some numerical evidence from, going years back, that often there's a spin liquid phase between the VBS and AFM. So then it would be natural that that spin liquid also ends at that point. Okay, so now it turns out that these JQ models all have weak first order transitions. But in some cases, like the JQ2 model, it's really very weakly first order, so that we believe that we can actually extract scaling dimensions. But it will actually be, very important in the end that we don't, if we tune a single model parameter, for example, we tune J over QN being one of these, then we actually cross slightly on the first order side of the transition here, okay? But then, what's the role of all these different Q terms? Well, how far away do we actually cross? So with JQ2, we cross, very close to the critical point. So it's the most convenient model for actually extracting scaling dimensions. But then if we go to Q3, Q4, and so on, and we did all the way up to Q6, we can actually move further up here, or maybe it's moving up here, but I just show it here. So there's another way to do that also more continuously. Namely, we can combine, for example, the JQ2 model with Q6. Then, as a function of Q6, we can move higher up here. So it's like this whole line is continuously pushed higher up. Okay, so that's the setup. And then what we are doing, Shai already showed a similar table. These are the scaling dimensions that we get, and these are the results from that paper. So Shai also showed a more recent result where this scaling dimension of the order parameter was closer to our value here, and that also brought all these other ones closer. And this is what Inchen talked about today. I want to point out one thing here from the beginning. We can also calculate the scaling dimension of the current operator, and that's a very nice test, because if it is a CFT with SO5, well, we know that the scaling dimension should be 2. Well, with any continuous symmetry, I guess, but it's a good test. Okay, so those are important results that we get. But there's more to this story than just these scaling dimensions. Namely, when we actually cross the transition on the first order line, what we have demonstrated is that there's actually a new emergent length scale that you would not necessarily immediately predict when you just see the scaling dimensions. So there's this exponent that we call nu star, which is related to the singlet correlation length and the traceless correlation exponent in this way. And this is related to one of these irrelevant scaling dimensions. Okay, so I will try to say a little bit about how we get these scaling dimensions and where this comes from. But it's basically quite a non-linear story in the sense that there are many components that you need to put together to get to this point. So even in the paper, if you look at this, there's some quantities that are computed that are eventually needed here, but maybe it's not clear why it's done until later on, although, of course, in the paper we try to explain it. But anyway, just to say it's sort of a non-linear story. Okay, so let's look at the order parameter and the correlation functions related to the order parameter. So Inchen mentioned this morning that there was no real concrete evidence of first order transitions in these models. It was more like, okay, something looks a bit odd in terms of the scaling. But now we actually have what I would say is very strong evidence for first order transitions. And I should say that John also had a paper a couple of years ago, which I think was the strongest evidence so far of there being an actual first order transition, not just anomalous scaling. And by the way, let me say from the outset that these two are not mutually exclusive. It turns out in the end there's a weak first order transition and anomalous scaling. Okay? Anyway, so if we look at the correlation functions, spin and dimer correlation functions that correspond to these order parameters at the longest distance of a square lattice, or at least along one direction, and we plot those as a function of 1 over L. So here's spin and here is dimer. You see that they go to what looks like, very close to 0. So, you would think that this is probably a critical system if you just look not very closely. But if you do blow up this region here, you will see that these points look more likely that they are actually hitting slightly above 0. So these are 3 values of the coupling we can vary in the model that are close to the transition. So you start to see that they split off a little bit here, You see it more in the dimer correlations, and it's in such a way that when the dimer correlation starts to dip down here, the red points, it starts to go slightly up there. So the sort of actual critical point should be somewhere, or transition point should be somewhere in between, and these are just some rough extrapolations for visualization. The point is that these values are very, very small, right? So you can imagine that, that there's some long-range order in the system, but if you use smaller sizes, the correlations will not be much affected by the fact that eventually it doesn't hit zero here, so that you could extract, still the critical exponent corresponding to these. Now, if we go to the JQ4 model as an example of, where, for example, this value here is a little bit larger. You see here it's like 10 times larger, and maybe here it's more clear that, the red point is a bit on the null side, because this is the spin This is the spin correlation function, and it starts to, level off there. Here it dives down. Okay, so from this we see that these JQN models have increasingly strong first-order transitions as a function of n, but even for n equals 4, they are still what I would say quite weak first-order transitions. Now, if we look at the correlations in a different way, we just take some big systems and look as a function of distance on that system. And spin and VBS in the same graphs, and JQ2, JQ3, JQ4. So it has been, as also was mentioned in talks today, this exponent eta 0.26, which corresponds to delta 5.63, which was the input in Schei's and Ning's calculation. That they took from Nahum et al., and they looked at a different model, the loop model, but actually even in my first paper on the JQ model, I had exactly that value, well, with an error bar which was a bit bigger than Nahum et al., but their loop model and the JQ model have always given very similar results, and it's quite natural because they are quite similar in some way. Anyway, so these lines here correspond to this exponent 0.63, and you see that definitely the fact that there's finally long-range order shows up pretty clearly here. But then Nahum et al., they had a very interesting suggestion, namely you can imagine that these curves here, they consist of something that depends mainly on R, and then something that depends mainly on the system size L, maybe down here. So if you take the derivative, you may get rid of any component that only depends on the system size. So we followed what they did, just taking the numerical first derivative, and you can see here the scaling looks much better. You're much less affected by this leveling off here, because that's something that depends mainly on L. So you get what looks like quite good scaling here. And these lines have exactly the same slope in all these three models. And we saw that this one is much more first order like, but still, it shows the same kind of criticality, because at these shorter distances, that eventual long range order is not yet very much affecting the results. So now I will not bore you with details, but we have looked at, this is more like a way of visualizing what I just said, but in the end, one should look very carefully at all of these things and also include some subleading corrections. For example, here you see that there's some deviations which I think come from the first descendant of the order parameter in the CFT. So after a lot of analysis that you can read about in this paper, this is our result, which is a little bit different from that. Okay, so then we have also calculated many other scaling dimensions. From different correlation functions. So let me show a few of them. So one is we want to get the scaling dimension delta t and also delta s, which should come from some full operator that's fully symmetric under the symmetries of our Hamiltonian. So for reasons that I cannot explain in detail here, now we take these z-type 4 spin operators, and we sum them up on a little plaquette like that, so to have a fully C4 invariant operator. and then we compute its correlation function, which we actually already did in this paper, where we in fact already proposed that there's multicriticality in the model, but we had misidentified one scaling exponent. But anyway, so the correlation function of this kind of operator, the sum of all of this correlated with one at some distance r away, is shown here for both the JQ2 and JQ3 model, and also both at distance r equals L divided by 2, for small systems, and also for r much less than L on big systems, up around 3 to 400, something like that. And you see that they all behave in the same way, and that gives the scaling dimension here, which is basically the slope eventually here. But you can see that there's also clearly corrections to that form, and in principle that could be the sign of the delta S, because delta S is larger, so it should also contribute, the singlet should also contribute to this correlation function. And in fact, if we, we fit it with 2 power laws, as shown by these curves here. But the problem is that it turns out that the first descendant of the T operator, delta T plus 1, is actually very close to what this is supposed to be and what we also finally think it should be. So from this we cannot actually tell, we cannot separate them because they are too close to each other. So from this we only get delta T. Okay, so this operator, which is something where, J, it's a Heisenberg type operator on a cell, which is modulated in this way. So we can actually argue that this contains the conserved current operator. Yeah, Inchen, you have a question? Yeah, so, this is what we also talk about a lot in the paper. It's actually very stable, yeah. Of course, if you include only more bigger sizes, the error bar goes up definitely. So I still hope to improve this a little bit. Okay, so this contains the current operator. So the correlation function of that should decay like 1 over r to the 4th. The scaling dimension should be 2. And, these are results for different sizes, but let's just look at the red points here. That's where we do the fitting, the biggest size. And it gives something very close to 2. So I think that should at least it gives me some confidence that all this makes sense. There's no sort of big problem with the fact that the transition is eventually first order. Up to some very large scales, it looks like it's critical. Okay, now let me talk about emergent symmetries. So, as has been mentioned, this SO5 symmetry, as first pointed out by Nahum et al. Even before that, we know that we knew that we had emergent U1 symmetry of the VBS. So if you look at in the simulation the distribution of the x and y components of the VBS order parameter, if we sit close to the critical point, this looks circular. So U1 symmetric, and when we go further into the VBS, finally we see these 4 dots corresponding to Z4. So now we have analyzed results like this more carefully because they can give us the scaling dimension of this lattice perturbation that perturbs this U1 symmetry. So we look at something like that we call phi 4. So we just take points in our simulations and accumulate these values. And then, we also have a paper where we do something like this for clock models and show that this definitely works. It gives us the correct exponents. So here I show this as a function of system size and using actually, what we call projector QMC for the ground state, and also the SSC method where the temperature is scaled so that we also get the ground state. Let's look at these. When we fit a line here, we get this y4 is minus 0.72, which corresponds to delta 4 around 3.72. Okay, so that was yeah, please.
So all these JQ models, they all have Z4 symmetry in the UV?
Yes.
Why Z4?
Well, because they all sit on the square lattice, they all have these.
So you could use a different lattice which would have maybe had T3 symmetry.
Yeah, so we could do the honeycomb lattice, but yeah, we can discuss that. Other people have done that. In this case, we just completely focused on the square lattice. Yeah.
That would allow you to speed up your scaling dimension.
Yeah, so yeah, exactly. So yeah, I know you're interested in the scaling dimension corresponding to 3 here, right? Which you could get on the honeycomb lattice. That is supposed to be relevant, right? So then this method doesn't work. So yeah, so this gives me the opportunity to say a bit more about this method. So normally people extract this kind of scaling dimensions also from correlation functions, right? But in this case, we don't have to do that because the perturbation is already in the model. It's not like we take a model with a perfect symmetry and we say, okay, what is the correlation function that gives this scaling dimension? We already have a perturbation in the model, so then we can use basically what comes from RG. You have a weak perturbation there, and then the question is, does the effect grow or shrink as a function of system size, or length scale, in this case, system size? So this is why we get these slopes here that correspond to y, which is much better than a correlation function which decays like 1 over r to this one times 2. So that correlation function decays horrendously fast and it's very hard to analyze. But this is actually very easy to analyze. But in the honeycomb lattice, this should eventually turn up because it's relevant, and then the question is even, can you even get the value that way? Okay, so that was the part where the lattice is perturbing the VBS. Now it's not so clear how that perturbs the other components of SO5. Of course, we always have a SO3 exactly for the Nell order, but the cross correlations, let's say. So this is our SO5 type order parameter, and now we can follow Nahum et al. Use the quantity, one of the quantities they used to argue for SO5 in the loop model. So this is basically a similar quantity we use, but there's an R here, which is the length of the vector. But it probes the same kind of angular dependence. But now this is the angle between one component, let's say mz of the Nell, and one component like dx of the VBS. So they already showed that this kind of quantity is very small, close to 0 in the loop model, but they actually didn't analyze their data in the way that we think one should do to get scaling dimensions. So here is basically F4 as a function of j over q in, this is actually in the JQ3 model, it doesn't really matter. And you see that it has a peak there, and the critical point is, or transition point is around here. So now we can see how does that peak value decay as a function of the system size. And we can also, well, okay, I should show that first actually. So that is shown here for all of these models, JQ2, JQ3, JQ4. So this is basically the value at the transition point, or you can think of it as the peak value there. And it decays like that. Same for JQ2 and JQ3, but then eventually the JQ3 model starts to deviate from this fitted line and the JQ model as well. And the JQ4 model, doesn't really show any good scaling at all. So what's going on here? So what we believe is, since we are sitting on the first order line, eventually when the system becomes really big, the SO5 symmetry actually becomes violated. It doesn't hold anymore. It's not very strongly violated here. These values are very small. But, the deviation from this line happens, before for JQ3 than for JQ2. So the JQ3 is slightly more first order, and this one is, really much more first order. But a very interesting point is here, what's the slope of this line? It's actually one higher than what I showed you before. Before we had one that had slope minus 0.72, and this one has a slope which within statistical error is exactly 1 away from that. So the previous scaling dimension was 3.72, and this one is 4.72. So we believe that this is basically the descendant of that one. So when when the lattice perturbs the VBS, it induces a sort of secondary effect only that perturbs or causes asymmetry between the components. That's our interpretation of that. Yeah.
So the perturbation of descent is not going to exist in Hamiltonian because it's a total curve shape. So if you figure out entire system, it will just vanish.
So you're saying that the descendant of that VBS should not appear in the Hamiltonian? Is that it? Well, maybe we have to discuss that. As far as at least we have one operator that differs suspiciously close to one from the one. But yeah, I'm not an expert on that, so this is just our interpretation. But okay, yeah, so maybe we can discuss that after. I somehow think it must be, but. Okay, so now let's see. I'm thinking now is my slides in the right order, but let me jump to the next slide because I think maybe no, it's okay. Sorry. So I had mentioned, in the beginning. Well, okay, no, it's this slide here. Sorry. So when we do a collapse of this data here, okay, so then we have to multiply this F4 by L to this power here to get this tip to not be size dependent. But then you see some scaling collapse builds up here. But that's if we scale the data with what I call nu star. Okay, so I had mentioned this nu star in the beginning. It's this emergent controls this emergent length scale. So now I'm just showing you. Okay, it scales with that, and the value of that is something like 1 over nu star is 2.4. So now we will talk about that a bit more. So what is that nu star that makes this collapse? Because it actually doesn't fit with anything that you would expect from the CFT. The value 2.4 is not like that. So I think I should go a bit faster. So our arguments makes a sort of detour here through the case that we do not think we have, namely a coexistence phase. So there's some old work on ON points with emergent symmetry, meaning ON is not an exact symmetry, but emergent, pretty close to what we have here. And then so if you have two order parameters and they have some effective interactions in the Landau theory, and that interaction is attractive, then you get a coexistence phase. So what was calculated in this old paper here is basically the shape of these phase boundaries to the coexisting ordered phase. And yeah. So in our case, phi A and phi B would be the AFM and VBS order parameter. Okay, so you would have an ON1 phase meeting an ON2 phase, so N1 and then. Yeah, exactly. Which actually we know that this is actually not possible, right? At this point, I guess they thought that you could have N1 and N2 and you have emergent. But now, there's a lot of work on that and it's believed not to be possible. There's always some relevant perturbations, unless N1 equals N2 equals 1. But anyway, what they did formally should still be okay. So if this V is negative, you should get a coexistence phase, and the phase boundaries are given by that. And now I translate this to our notation, applying if this is the SO5. So then this psi should be this YT, which is 1 over nu t, minus this Y4 prime that I mentioned to you before. Okay, so what we are proposing is that here it shouldn't really matter in a scaling sense whether this V is positive or negative. So if we have repulsive interactions, which we believe we do, and we have some way of detecting that, but I don't have time to talk about it, then we don't have a coexistence phase. But we have some region here in this phase diagram where the repulsive interactions between the order parameters start to break down the SO5 symmetry. Okay? So then we just take this and then we translate it to finite size scaling by saying, okay, this kind of region, which is now not a phase, but it's a region, has some width. And then that width, if you go to s equals 0, that width translates as a finite size width. So basically the width as a function of s should scale in this way, just following from that. And then one can translate that to finite size scaling. This is just the very standard way to go from thermodynamic scaling, limit scaling to finite size scaling. So then we claim that there's this new star that is related to this psi and this new s, the singlet new exponent in that way. So this is similar data I showed you before, but just to emphasize, okay, how can we define that width? It's very convenient because this F4 goes through 0 twice, so we can just take the distance between those points and scale that as a function of system size. And again, we do JQ3 model, JQ2 model, different methods just to show that everything is so consistent, and then we get this 1 over nu 2.4. And that was the value I showed in the scaling here as well, so we have a scaling collapse. Okay, so that's the meaning of that. But now the important point, and I guess, there were some questions already, so I add some minutes to my talk because some minutes were already taken by questions. Okay, so I should go back one step. So now the point is that we had a hard time, determining the scaling dimension delta s, which determines nu s as well. But if we believe what I did here, we have a prediction that allows us to extract delta s from this 2.4 value and from also, these that I told you about before. So the prediction is that one. Okay, so now the question is, does that work? So now we can use the kind of results that Shai mentioned, but they only have results for a couple of points. But there's another paper that does some of that, some of those bounds in, for example, in the plane delta phi and delta s. And also they do he did the plane delta phi and delta t, but here is the one relevant for what we are discussing now. And in this paper it was actually SO5, SO6, 7, and 8. So if you look at the SO5 bound, then I take the values we get for delta s from this prediction and the delta phi that we had before, and then that's roughly this little red area here. And you see that within 2 error bars, we actually agree with this line. Not within 1 error bar, but within 2 error bars is already considered okay, in my mind at least. Now I'm not 100% sure that these boundaries correspond exactly to what Shai and Ning Su have. It looks to me when I take this one of their points that it's actually not exactly the same, but maybe we can discuss that later. At least it seems to make some sense here. And also if we compare with this other plane that's published here, we also have a 2 sigma agreement. Okay, so now can I take like 2 minutes and explain this? Yeah, 2 minutes. Yeah, exactly. So this is pretty much my last slide here. So, one interesting consequence of this new star exponent is that it controls a length scale on the way to the first order transition. So what I graph here, this is just a very schematic thing, but you have the log of the correlation length on a scale of log 1 over g. So g would be 0 at the critical point, so when you go towards the transition, you go to the right hand. So if you sit at the critical point exactly at this SO5 CFT, then you should see the correlation length, and this is, when you, let's say, approach from the AFM phase, you approach the transition into the VBS, you grow like that. But what we are arguing is that if you are a little bit on the first order line, there's actually a crossover to another growing form of the correlation length before the saturation of the correlation length when you actually go to the transition point. And this has actually been seen even before. We have our own data, but let me show you data from Nahum et al., where they actually computed the correlation length, supposedly in the thermodynamic limit by extrapolations and so on. And we took their data from their paper, scanned it and regraphed it in the way to illustrate what we have here. So you see that they see a growth here of the correlation length, which fits exactly, or it fits very well with the exponent mu t. Okay, and then when they come closer to the transition, it crosses over and it fits very well with this new star. And they had this data, but they didn't know where it comes from. They said just, okay, eventually the correlation length grows like that, and this is something else. But now we understand it as actually this kind of crossover. And again, that's the exponent. Now, I didn't have time to well, so okay, so the point here still is that, okay, we sit slightly on the first order line. We get some, let's say, weird behaviors that seem to not fit with the CFT, but actually the CFT still can explain all the behaviors. Now, just a preview, I will not talk about it, but we can also go into the first order line with this JQ2, Q6 model, and we can see how the order parameters grow there, and it fits also very well, with the CFT prediction. Okay, so I will stop there. Thank you.
Thank you, Anders. It's really great you guys go to the reports. Can you go back to the reference by Lee?
Yeah.
So here, different lines correspond to SO5, SO6, SO7?
That's right.
Oh, so the SO6 line is related to the N4 QED, is that right?
Yeah, actually, I don't know. Maybe he did all these for some good reasons, I'm sure, but I forget what the reason was.
What? It does, right? Yeah. Okay. Okay, fine. Yeah.
Yeah.
What would be a good physical observable to see this to scaling behavior? Specific heat at finite temperature, spectral function?
Yeah, actually many things. So in this old work by Nahum et al., they looked at many quantities, and essentially in all the quantities they found this crossover. And in my previous works, I had also seen this kind of crossover. And in the paper, we have other examples as well. So for example, one quantity that had been sort of a smoking gun for first order transition for a long time was the spin stiffness. You look at the finite size scaling of the spin stiffness, and that didn't seem to behave as it should. And then it was suggested that it's a first order transition. Well, that turns out to be the true, but this weirdness that is seen is not just that it doesn't go to zero as a function of size at the critical point. There's also a sort of crossover behavior which exactly has to do with that, which we already had a paper about in a few years ago, but then we did not understand what this new star was, and now we understand that we can derive it in this way. But it should affect basically all quantities that depend on the correlation length in some way will be affected by this crossover.
So like measuring something like neutron scattering, if you
measure I think so.
You see some anomalous softening of spin waves or whatever.
Something like that. Anything that depends on the correlation length.
Thank you.
Yeah.
Well, it seems that all of the data you showed is on the first order side of the DQCP.
Yeah.
Do you have any data on the other side?
Yeah, so I don't have any data as of yet. So the problem is, okay, maybe I can show it in this last graph that I just flashed here. So, when we look at, this phase diagram, where we have the JQ2 model, so the critical or the transition point that I discussed was there, but then we can go up with QS, and now, this singlet scaling dimension should affect what's going on here. Now we can fit data here, which gives us a negative value of the critical point, because even at Q6 equals 0, the order parameter is not exactly 0, but it's very small. So what we would like to do is to go to this side, but there our QMC simulations have sign problems, so we cannot do it. But we try to do it in other ways. So we can do DMRG. So for example, now this Q6 operator is very big. It's not so nice to, I think, implement in DMRG. But we can use some other couplings. So for example, we can combine the JQ2 model with the J2 interaction, that you know very well, the next nearest neighbor frustrated interaction. And then something similar should happen. So we can, by turning on J2, I think we can reach that kind of point. But of course, then it's still hard because we have to do DMRG, or now we are also trying some machine learning approaches and whatnot. But of course, there's evidence from lots of previous works that we actually have this kind of phase diagram here, right? That there's a spin liquid in the J1, J2 model, for example, between VBS and AFM. And then you can imagine if you add a little bit of Q interaction to the J1, J2, that spin liquid will close, and eventually that's the critical point. But of course, it doesn't have to be like that. There could also be like this applies, and then the spin liquid opens only later, so then there could be another tricritical point there. I don't know, but so short answer to your question, no, we don't have any concrete results, and I think we will never get anything as good as we have here, but we are trying very hard to see if we can push this line down and do something.
Okay, thanks.
Sorry, I want to ask a little bit more about this singlet relevant dimension, this 2.27 you got.
Yeah.
How does that number look like if you, on JQ2 versus JQ3, JQ4?
Yeah, right. So I guess we haven't really done too much on that. So for this scaling dimension, well, I mean, we have this, right? So this one of a new star, you see there are results here for JQ2 and JQ3, and they give very close to the same result. So if we use that result, then we get the same new star. But of course, we would like something independently of that, and one independent result is exactly extrapolating the order parameters to infinite size, which is not easy, but and I don't think we can do it exactly, but maybe it's good enough. And then when we fit this value is consistent with the singlet dimension. But this we have not done for, well, I mean, this is for the JQ2, Q6 model, so we could also do it for Q3 here and do Q6, for example. We could do that, but that we haven't done. But I don't expect anything to be different. But it would be very nice, of course, if we could get the scaling dimension from, if somebody would tell me, this delta t plus 1 actually cannot appear in this correlation function, then this correction here would come from the singlet. And in fact, the value we get is consistent with the singlet or that one. I mean, we cannot tell because the error bars are pretty large on the second power law. But does anybody think that this would not appear here? I think it should, but yeah.
Do we have a last question before lunch?
Shai has a question there.
Okay. I assume there's no a priori reason why the CFT could not be embedded in a heterocritical phase diagram, right? So could one imagine, adding terms to the Hamiltonian such to reduce the repulsion between the order parameters?
Yeah, that's a good point. I haven't really thought about that, but yeah, maybe we could cook up some interactions that gives a coexistence phase. That's interesting.
Can you speak in the mic?
Could you summarize the evidence that it's SO5 symmetry as opposed to SU2 cross Q1? Because when you're computing all these things, you're kind of computing it for like a specific operator. Presumably, if you want to check SO5, you'd have to show that different operators have the same scaling dimension.
Yeah,
right?
but I guess just the fact that this decays, wouldn't that imply that it cannot be the lower symmetry that you mentioned? There's no reason that